All right, so got cut off there, but we're back to elastic collisions. Both momentum and conservation of or kinetic energy are conserved. When that's the case, not only do you have this equation up here conserved, but you have this one where 1/2 mv initial squared plus 1/2, that's m1, m2 v2 initial squared is equal to 1/2 m1 v final squared v1 final squared plus 1/2 m2 v2 final squared. So you got this equation and you have this equation up here. Both those have to work. So what you can do is you can solve for one and put it into the other one and make life easier. If we do this, we're going to say the same thing we did before. We're going to say that V2 initial is equal to 0. So we're going to do it in the V2 initial reference frame. And then we're going to end up with two equations. And this is what we'll probably do with all your problems, is just use these equations. This one is V1 final is equal to M1 minus M2 over M1 plus M2 times V1 initial. And then this is V2 final is equal to 2M1 over M1 plus M2 V1 initial. Okay, so make sure you know those two equations. This only works if it's an elastic collision. So when you're looking at your problems, if it says elastic collision, you're going to use these equations. If it doesn't say elastic collision, you cannot use these equations. It's only for that special case where it's an elastic collision. But let's look at these closer here. If you have two particles that are colliding with each other, two boxes, if mass 1 and mass 2, let's say they have the same mass. So mass 1 is going to run into mass 2. Mass 2 was not moving, so we fit this condition here. If they have the same mass, then M1 minus M2 is going to be equal to 0. And if M1 minus M2 is equal to 0, then V1 final is equal to 0. So what happens is the box that's coming in with its initial velocity here, that box M1 is going to hit the other box and stop. And then over here, you can have 2M1, but M1 and M2 are the same, so this becomes 2M1 on the bottom, M1 plus M1, so you have 2M1 over 2M1, that just becomes 1, and V2 final is equal to V1 initial. So what happens is the momentum from M1 comes in, hits this box stops, and all the momentum goes to this box. Okay, which can occur if you have a perfectly elastic collision. This is when, if you've ever played pool before, the cue ball hits, stops, and then the cue ball rolls off at the same. Then the regular ball rolls off at the same. That only works if you don't have a cue ball that has more mass than the other one. If you play like in certain pool tables, sometimes they make the cue ball slightly more massive or slightly bigger, and it changes things. But let's look at the case where M1 is much bigger than M2. So M1 has more mass than M2. Well, if that's the case, then M1 minus M2 is going to be a positive value here. Okay? And when they hit, V1 initial is here. When it hits, M1 is going to keep going. So it hits, the smaller box is going to go off, but the big box is still going to keep moving. It's not going to stop. Okay? And because 2M1 up here, 2M1 is going to be bigger than M1 plus M2 because M2 is smaller than M1. V2 final is actually going to have a higher velocity than V1 initial. And so it comes in with a certain velocity, but the box, the smaller box, leaves with a higher velocity than the initial velocity coming in. The momentum is conserved, but the velocities have changed. You can do what they call creating an accelerator, where you have a very massive box and it hits a smaller box, which hits a smaller box, which hits a smaller box. Then the initial box will make that one faster, which will make that one faster, which will make that one faster, and you can increase the velocity very rapidly. And it works exactly the opposite if you have the other situation. If you have M1 here and you have M2, where M2 is bigger than M1, then this is going to be a negative value if M1 is smaller than M2. So the first box is going to come in like this. It's going to hit and it's going to bounce backwards. So it's going to hit and it's going to bounce off. And M2, because M1 is smaller than M2, this is going to be smaller than that. It's always going to go off with some fraction of the initial velocity. So if the initial velocity coming in is very high, this is going to go off with a much less lower velocity because it's more massive than the first one. All right, those are elastic collisions. Remember, when you do problems, you can only do problems that say elastic collision. All right, the last thing we have to know for this section is you have to be able to do this in 2 dimensions. Lots of times you may have a particle coming in like this. Here's mass 1 coming in with the velocity this way, v1 initial, and you may have another mass 2 coming in with its own initial velocity. They hit and then they bounce off each other. Okay? And so then M1 V1 final is this way and M2 V2 final is this way. Well, what you have to do is, what really has happened is it hit and it bounced that way, and this one hit and bounced up that way. So there was an interaction when they ran into each other. The only way to solve these problems is the way we always did it. We have to split it up into 2 dimensions. So you'd have to make your coordinates like an x coordinate there and a y coordinate here. This is the other way for the x coordinate. And then you'd have to break up all these velocities into components. So you have components this way, component this way, this one has a component this way, and a component this way, and this one has a component this way, and a component this way, and then you have to do x direction separate from y direction. So you're going to use this same equation right here, but you have to do 2 of them. One in the x direction, one in the y direction. And then you have to solve them independently. And then figure out what the velocity is at the end using the components. Because you'll end up with a v final in the x direction and a v final in the y direction. And to combine those to figure out the velocity, you have to take the square root of that. Like we've done before. This just goes all the way back to like chapter 3. But you got to remember, you have to do it in 2 dimensions. You have to do x direction separately than you do y direction. All right, if you can do that, you can do all of chapter 11. So go and do these problems right here. Problems 15, 25, 31, 47, and 58. And I will put up videos showing how to do each of those problems. If you can do all those, you should do okay.